Now, intensive properties are independent of the system size. So it doesn't matter how many different weights we have. It's not additive. We don't add them together depending on the number of weights or the amount of mass that we have of the system, right? So things like pressure and temperature are examples of intensive properties. So the temperature of the whole is not equal to the temperature of its parts, right? So if we have 10 weights that are 50 degrees each, the total temperature of all those weights is not 500 degrees, right? They're all 50 degrees. Same with, you could imagine, I don't know, if there were atmospheric pressure acting on the weights. The pressure is not additive for the multiple weights. Okay, so that's extensive properties versus intensive properties. And let's talk about equilibrium. So a state of complete balance is sort of a simple way of defining equilibrium. A system is in equilibrium if there are no changes in properties after isolating the system. And what we mean by isolating the system is, we talked about boundaries, the system, the boundary, and the surroundings. So if we isolate the system, it kind of means that we're drawing the boundary around the system so that we don't have any interaction with the surroundings. In this case, you can imagine having a, for instance, like a tank of air that maybe is at 100 psi or something like that. Well, our boundary would be drawn just around the edge of the tank. The tank itself would be at 100 psi, and assuming that we don't make any changes to the tank, it would stay at 100 psi. The tank of air would be in complete balance at 100 pounds per square inch. Here's an example of, you could imagine if you had a hot cup of coffee sitting on a countertop. In that case, we would not have an example of equilibrium simply because at that point the temperature, we would have properties that would be changing over time, right? So in the case of the coffee, the temperature would be decreasing as it sits there. After a long time, that hot coffee would then become the same temperature as the room, so room temperature coffee, right? If we had a glass of water, let's assume that it's at room temperature, then and at that point the temperature of the water would remain constant because it would be room temperature. The pressure acting on the water would be atmospheric pressure, and we're going to assume that the volume would stay the same, although technically if you had a glass of water sitting there long enough, you would have evaporation. So it's not perfect equilibrium, but that's about as close as it's a close example. So let's talk a little bit about units that we'll use in this class. Base units are a unit of which all other measurements are based, right? And so you've probably learned about this in other engineering courses, but the two major unit systems are SI and English units, right? So if we're looking at a quantity of mass in SI units, it would be kilogram, and in English units, it would be pound mass. You'll notice here it just says LB as the symbol. In my notes and throughout the class, I'll actually write it out as LB subscript M, just so it's clear that we're talking about pound mass. We'll talk a little bit about pound force here in a few moments, and so I always write it as LBM just so it's clear to differentiate from pound force, which is written as LBF. Okay, so our quantity for unit of length is meter in SI units and foot in English units. SI units, our time is in seconds, so same in English units. And then for force, we will have a Newton for SI units, which is a kilogram times meter per second squared, right? So it's a unit of mass times acceleration. So if you remember the equation, F equals ma, right? Force is equal to mass times acceleration. And then in English units, we have pound force, which is equal to 32.174 pound mass times feet per second squared, right? So again, we're doing force is equal to mass times acceleration. So we have 1 pound mass times the acceleration of 32.174 feet per second squared, right? So that gives us a pound force. So we can have secondary units derived from those base units. So it's a unit defined in terms of base units. One thing I will say in this class, units are very important. A lot of times students will miss points on exams and homeworks simply because the units are not correct, and it's very common. So the easiest way to make sure your units are correct is to make sure that you derive all of your calculations in terms of base units. So if you use base units, then you will always be able to see whether you are getting the final unit that you need. Secondary units that we will use in this class, so SI is the unit system that we'll use most commonly in this class. Secondary units are derived from the base units, and some examples here we have a Newton. A Newton is a unit of force, right? We mentioned this before. It's kilogram times meter per second squared. A unit of energy would be in joule in SI units, so a joule is equal to a Newton times a meter, so a force times a distance, and that's kilogram meter squared per second squared. And then a unit of power would be, an example of that would be, in SI units would be watt, so that's a time rate of change of energy, right? So if we take a joule and we divide it by a second, that's a time rate of change of energy per unit second. That would give us a watt, and that would be kilogram meter squared, and now divided by seconds cubed, right? And so those are some examples of secondary units that we will commonly use in this class that are derived from base units. So here's an example of a wind turbine. And I'll just read through the example. I suggest that you pause and take a look at this problem, try to solve it yourself before looking at the solutions. I put my lecture notes on Blackboard so you can see the solutions, but please just take a moment, think about the problem, see if you can work through it. And the goal of this problem isn't necessarily, we're not learning any new thermodynamic concepts, but really we're just starting to use our unit conversion sheet, which is also on Blackboard. So pull that up before you begin to work on this problem. I suggest that you take a few minutes to work through it, see if you can figure out the answer, and then you can look at the lecture notes. So a school is paying 9 cents per kilowatt hour for electric power. The school installs a wind turbine with a rated power of 30 kilowatts. If the turbine operates for 2,200 hours per year at the rated power, we want to determine the amount of electric energy generated and the money that's saved through the use of this wind turbine to produce electricity. So again, unit conversion sheet, make sure you open that up, take a few moments, get out a piece of paper and a pencil, and begin working on this. See if you can find the solution, and we'll go through the solution in the next video.